So today in Digital Labs, we're going to be working on lab number 12, Other Devices and Techniques. You can see our required parts. We're going to need the breadboard, the wire strippers, and our hookup wire. We're going to be using some gates we've used before, the 7408 AND gate, the 7414 Schmidt inverter, the 7447 BCD to 7 segment IC. Then we're going to be using the 7475 4-bit latch IC, which is new, the 74125, which is a 3-state buffer IC, that's new, and the 74157 2-line to 1-line multiplexer IC, which is new. The 74393 CMOS counter we used a couple labs ago. The 7-segment displays, we've used those before. We're going to need a red and green LED, 330 ohm resistors, 2K ohm resistor, 4.7K ohm SIP resistor. We need our dip switch, a 1 microfarad capacitor, and a 470 microfarad capacitor. As always, when I introduce you to a new IC, I give you a pinouts on that lab page. So the 7475, the 125, and the 157 pinouts are on this page. For the 7408, 14, 47, and 393, and the 7-segment displays, you're going to have to refer to your previous labs. Now I've given you some reference sections. Chapter 1, we know that's all about numbers, so that's binary, decimal, and hexadecimal numbering systems. And we'll have to take a look at Chapter 13, 13.1 to 13.5. And once you've completed this lab, you should be able to answer solve problems 13.1 all the way up to 13.30. So just as a little review, figure 1-7 is counting in decimal, binary, and hexadecimal number systems. So you might need to review that. So in Sham's Outlines, Digital Principles, 3rd edition, Chapter 13, talks about other devices and techniques. So section 13-2 talks about the data selector or multiplexers. And in figure 13.1, they give you a comparison of a rotary switch and a data selector. So all a multiplexer does is switch from one of the inputs and outputs it on the one output. So all it is really is a selector switch that's controlled electronically. So we have electronic data selector lines going into our multiplexer. So section 13-3 is about multiplexing displays, which is part of the lab we're going to be doing today. You can see we have a basic counter, so we have the ones counts and the tens counts. So we want to put them on 2 separate displays. So what we do is we send it through a multiplexer. So while we're selecting the ones, it goes through the decoder and comes out on the ones display. And then when we select the tens counter, the tens digit comes in, goes through the decoder, and comes out on the tens display. Now you notice we have a fast clock. It's running at 100 Hertz. So it's switching back and forth between the 2 displays at 100 Hertz. And it's also switching our multiplexer back and forth between the ones and tens at 100 Hertz. Running at 100 Hertz, we should not see any blinking on the displays, so it should look like both displays are on all the time. So when you flip the page and look at figure 13-6, this is the circuit that we're going to be building today. Instead of using a 555 timer, we're going to use the Schmidt inverter as a clock signal. Section 13-4 talks about demultiplexers. So we saw what a multiplexer was. Now we have to take our input and demultiplex it out to our output lines. So if we had 7 or 8 input lines, then we have to have our 7 or 8 output lines, and we have one transmission line. And if we rotate our selector switches fast enough, looking at the outputs, you'll not see any different from the inputs. And lastly, section 13-5 talks about latches and three-state buffers. And if you take a brief look at figure 13-11, they give you an example of a microprocessor using a three-state buffer to talk to the data bus. We also have a keyboard that goes through a three-state buffer onto the data bus. We also have our RAM memory that has to go through a three-state buffer to get to the data bus. So when our microprocessor is taking input from the keyboard, the three-state buffer is activated on the keyboard and the microprocessor so they can use the data lines. When the microprocessor is storing data to memory, it needs to activate its buffer and the buffer for the RAM chip. We don't want the keyboard data messing up the data on the RAM. So that's where tri-state buffers are used. So if you take a look at figure 13-12, A part, it shows you the logic symbol of a three-state buffer. It looks a bit like an inverter, but it doesn't do any inverting. Basically, when the control line is active, whatever's on your data will show out on your output, and you can see it's non-inverted. Now when the control line goes high, according to the truth table here, we have an output of high impedance or very high resistance. What that means is this circuit is basically disconnected from whatever it was connected to. So looking at our lab schematic for part A, it talks about latches and three-state buffers. So what we're going to do is use the 7475, and you can see we have three switches on here. So the 7475 is a latch. So basically what it's going to do is we're going to put data into it, we're going to enable it, and we should be able to store something here even though the data is changing. So that's the purpose of a latch, is basic to store something. So it acts like a memory. Then we're going to use the 74125, which is a three-state buffer IC. So we've got a control line for it. So basically we should be able to get our data to pass through it, and we should be able to disconnect it. So remembering from lab number way back where we did basic logic, you can see on our circuit here, if we put a logic 0, the green LED should go on. +5 should flow through the 330 through the green LED to the logic 0. If we put a logic 1 here, logic 1 should flow through the red LED through the 330 ohm to ground. So the red LED should be on, and because we have +5 on both sides of the green LED should be off. Now when we activate this control line, it should disconnect the 125 from our two LEDs. So if the 125 is disconnected from our two LEDs, we're left with a circuit that has 5 volts driving current through the 330 ohm, through the green LED, through the red LED, through the second 330 ohm to ground. So when the circuit is disconnected from the LEDs, both LEDs should be on. So under procedure, part A, we're to fill in the pin numbers above, construct and test the circuit, then complete the truth table above using 1s or 0s, or NC for no connection. Figure 1310 contains the latch. Figure 1312 contains the three-state buffer. Switch C is used for control, and if C equals 1, there is no output from the 74125. Thus, both LEDs will be on, indicating no connection. The circuit is electronically disconnected from the output. If C equals 0, the output of the 74125 will be either 1 or 0. Only one LED will be on. Switch D is the data, 1 or 0. Switch L is used to latch the data into the 7475. If C equals 0 and L equals 1, the output will equal D. If C equals 0 and L equals 0, then the output will be latched, and changing D will have no effect on the output. When you're looking at the pinout for the 7475, I just wanted you to be aware that the ground pin is on pin 12. VCC is on pin 5. So it's kind of an odd arrangement that we don't normally see. The first latch, the Q is on 16, the Q0 is on 1, and the D is on pin 2. I want you to notice that pin 13 is the enable, and it's the enable for latch 1 and 2. So both latches are enabled together. Pin 4 is the enable for latch 3 and 4, so 3 and 4 are enabled together. When you look at the pinout for the 74125, normally we think of the input as being on 1, but the control line is on pin 1. The input is on pin 2 and the output is on pin 3. So filling in my pin numbers for the 7475, the D input is actually on pin 2. The Q output is on pin 16. And the enable line is actually labeled G, which probably represents gate, and that is on pin 13. Please notice that VCC is on pin 5 and ground is on pin 12. For the 74125, the input is on 2, the output is on 3, and its enable line is on pin 1. So you can see when L is enabling the 7475, that's active high. So that's a 1. And to enable the 74125, you can see there's a little bubble there, so that has to be a low, so that has to be 0. Then whatever is on the D key, or the D switch on 2, should show up on 3. So if we have a logic 1 coming out on pin 3, the red LED should be on, and if we have a logic 0, the green LED should be on. And if the 74125 is not enabled, then it should be basically disconnected from the circuit, and the green LED and the red LED should both be on, but slightly dimmer. So this is my completed circuit, and you can see I have my 2 LEDs, and right now I have all my dip switches in the down position, and you can see I'm outputting a logic 0. That's the green LED being on. Now my dip switches are set up so that this is my D, this is my latch, And the last one is my control line. So if I move my data switch to logic 1, you'll notice the output doesn't change. So if I move my latch to logic 1, you can see my output changes. So if I move my D switch, you can see my output's low. And when I move my D switch, you can see my output's high. If I want to latch the circuit, I move the latch to logic 0. So now it's latched. So now when I change my data, I've changed my data to 0. You can still see the output is high. If I change my latch to logic 1, you can see my output is now logic 0. So right now, the data is allowed to flow freely through the circuit. When I enable the latch, whatever was in the latch is now stored. So when I change my data, you'll notice there's no change on the latch. Now my control line is at logic 0, meaning the 74125 is connected to the two LEDs. When I move the control line to logic 1, you can see I no longer have a logic 0 or a logic 1. Both LEDs are on and they're dim. So basically the 125 has disconnected my latch from the two LEDs. So looking at our truth table, we can see that L is going to be 1, so that enables the 7475. C is going to be 0, so that enables the 74125. So whatever's on D should show up on the output. So if D is 0, the green LED should be on, the red LED should be off. If D is 1, the green LED is off, and the red LED is on. In the next line of the truth table, we are in the latch state. That means that L is now 0, which means the 7475 is no longer enabled. It's now in the latch state. So whatever was on the output should remain on the output, regardless of how we change our data. So in both cases, the green LED will be off and the red LED will be on. In the tri-state cases, the 74125, that's key C, is now a logic 1, meaning that the 74125 is now in high impedance mode or disconnected from the circuit. In this case, no matter what switch D or switch L are, both the green LED and the red LED are on, indicating no connection for each of our lines in our truth table. So once you have wired up your circuit and verified that it is working, demonstrate it to your instructor so they can initial it to indicate that it is complete. So under Lab Schematic Part B, we're going to be doing the multiplexing displays. So hopefully you recognize the two 393 counters from our previous counter lab. The first one's going to count 0 to 5, and the second one counts 0 to 9. So what we've got here is a 60-second counter. The outputs from the counter are going to go through a 157, which is a multiplexer. So we're going to select between the A inputs coming out on our outputs or the B inputs coming out on our outputs. It's going to go to a single 7447, and that looks like it's some kind of BCD to 7-segment display decoder, and that's going to come out and go to both 7-segment displays. So we've got our 1 Hertz clock and we have a 400 Hertz clock. So we're going to be switching back and forth between the two displays, and you'll notice there's an inverter in the line here. So when it's logic 1, it turns on this display. When it's logic 0, it gets inverted and turns on this display. The same clock comes down and activates our multiplexer, selecting between the A group or the B group. So under the procedure for Part B, we're to use the circuit of Lab 9B to generate U1 at 1 Hertz. For the second clock, U2 at 400 Hertz, we're going to use an R of 2 k ohms and a C of 1 microfarad. We're to fill in the pin numbers, construct and test the circuit, and the circuit must count from 00 to 59, then reset back to 00 and count again. So for the schematic for Part B, you can see I've filled in all my pin numbers. And then as I've connected each of the lines, I've highlighted the line to indicate that I've connected it. Some of these lines are crossing each other, so it's going to get quite confusing. So I highly recommend that you highlight a line once you've hooked it up on your trainer. So this is my completed circuit. At this end of my circuit I have the 7414. So you can see I have a slow clock hooked up at this side. So this is my 1 Hertz clock. On this side I have my fast clock, or 400 Hertz. Notice I didn't bother hooking up an LED to it because it would blink so fast I wouldn't see it blinking. I have all my ICs lined up here. One of the things to note about this circuit is even though it is a fairly complicated circuit to wire up, if you put them in one line at a time and highlight each line that you've put in, you shouldn't have a problem wiring up the circuit. It's also important to keep your lines as neat as possible. You don't want a whole jumble of wires running back and forth across all the ICs, and then you can't see if one has fallen out. So keeping your circuit neat is the trick to building a successful project. So I just wanted to show you a close-up of my main circuit. You can see at this end I have my 7414, and I'm actually going to use 3 of the inverters in here. So the first inverter is for my slow clock that's running at 1 Hertz. My next inverter is for the fast clock running at 400 Hertz. The third inverter switches between the two displays. So you can see the 400 comes out, goes into an inverter, and comes out. So these two lines are selecting between the two 7-segment displays. The next IC is the 393, and that's a binary counter, a dual binary counter. So one is being used to count from 0 to 9, the other one counts 0 to 5. The next IC down is my 7408, which is the AND gate, which I use to decode the output from the 393 and reset it when it gets to 9, or reset it when it gets to 5. So the reset line is actually going on the 10 count or the 6 count. My next IC down is a 74157, and that's a 2-line to 1-line multiplexer. So that's switching between the two different counters that are counting. So out of the 74157, it goes into the 7447, which is the BCD to 7 segment driver. So the 7447 is driving both 7 segment displays. So they're actually hooked up in parallel. So pin 1 of the first display goes to pin 1. The second display goes to pin 13 of the 47. Now which display is being activated is determined by the 2 yellow lines coming from the fast clock. You'll notice I have my 330 ohm resistors in there, and they actually go to that clock signal. I also have the power on indicator. It's very important because you never know, you might not wire up the circuit correctly the first time and you may get no output, and it's important to know that power is getting to the circuit. So looking at the count sequence, you can see this is my least significant digit. Right now I'm at 3. This is my most significant digit. Already it's at 5. So that's 57, 58, 59, and at 60 it resets to 0, 0, and then starts counting up again. So once you've wired up part B of your circuit and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. So on the last page of the lab, we have 7 questions for you to answer and hand in. If you are looking for answers, open your textbook. Page 1 of the lab shows some hints, and those hints are in the Solve Problems 13.1 to 13.30. So this is a close-up of my count sequence. You can see the lower digit is my ones digit, and it just reached 59 and went back to 0, 0. I also have a power on indicator just to indicate the power is getting to my breadboard, because if after hooking up this circuit nothing works, we need to know if power is getting to our trainer. So there's 18, 19, 20, 21, 22, 23, 24, 25, 29, 30, 31, 39, 40, 41, 49, 50, 51, 59, 60, 1.